Here we're given a common emitter configuration with the following values. The transistor has a beta, our current gain, of 100 RB. At the base of the transistor is 100 kilo ohms. RC at the collector is 1 kilo ohm. We're supplying a voltage to this transistor of VCC of 5 volts, and Vs is equal to 2 volts for the first case, and in the second case Vs is equal to 6 volts. We also note here that VBE from the base emitter voltage is equal to V gamma, which is equal to 0.7 volts. Given these parameters, we're asked to find the collector current IC and the voltage across this transistor between the collector terminal and the emitter terminal, or VCE. To solve this circuit, we note that Vs is equal to 2 volts, which is greater than V gamma of 0.7 volts. Therefore, the transistor is not in cutoff mode. So at Vs is equal to 2 volt, transistor is not in cutoff mode. Therefore, we can find the collector current IC. First we note IC equals beta IB. So we'll find IB, noting that the voltage across this resistor RB is Vs minus VBE. So therefore IC is equal to beta multiplied by the voltage across RB, which is Vs, minus V gamma, which is equal to VBE, all over RB. Substituting the values of for beta 100, Vs for 2, V gamma for 0.7, and RB for 100 kilo ohms, we have IC equal to 1.3 milliamps when it's not in cutoff mode. So we assume here that is in the active region. Now note that the available short circuit current is what we supply when VCE is equal to 0. So I short circuit current is essentially VCC divided by RC, which is equal to 5 volts divided by 1K, or 5 milliamps. So we note that IC is less than ISC, and therefore we can say that it is in active mode. Now we can use the following equation where VCE is equal to VCC minus the voltage drop across the collector resistor RC. So it's IC using Ohm's law times RC, which is equal to 5 minus IC, which we found to be 1.3 milliamps, multiplied by RC, which is 1 kilo ohm. That results in a value of 3.7 volts. So for Vs equal to 2 volts, we see that the transistor is in active mode, and the outputs for this configuration is that IC is equal to 1.3 milliamps and VCE is equal to 3.7 volts. So let me highlight that result for Vs equal to 2. So VCE is 3.7 and IC is equal to 1.3 milliamps for a voltage of Vs is equal to 2 volts. Now let's look at the second case when Vs is equal to 6 volts. And when Vs is equal to 6 volts, that implies, and we assume that the transistor is in active mode. So here, let's calculate the collector current IC. So IC, in essence, is, we're going to do a similar result right here, beta Vs minus V gamma divided by RB, and we note that this expression is equal to IB. Substituting the values, we have 100, 6 minus 0.7 all over 100 times 10 to the third. And that's equal to 5.3 milliamps. Let me highlight that. 5.3 milliamps. Now we compare it to our collector current for the short circuit case, and it's 5 milliamps. Because our collector current is greater than our short circuit current, then we can say that the transistor is in the saturation mode. And what's in the saturation mode, so we know that it's in the saturation mode, and that implies that IS is equal to the I short circuit current, which is equal to 5 milliamps. And that VCE is equal to 0 volts. So in essence, we tried two different voltages, one at 2 volts, and we assume it's active mode, and it turns out to be so. And that IC is 1.3 milliamps, which is less than the 5 milliamp that's the short circuit current. Now when Vs is 6 volts, we see that this is conducting. However, IC, according to these calculations, exceeded to the short circuit current of 5 milliamps when we calculated here for Vs is equal to 6 volts to be 5.3 milliamps. That implies it's in saturation mode, which implies that IS is equal to the ISC, the short circuit current, equals 5 milliamps, and that VCE is equal to 0 volts.